Hello, guys. Welcome to the last episode of Electricity and Magnetism. So we're going to talk about hydro transmission lines and why your hydro bills cost as much as they do. All right. Just to let you know, the way how electricity is delivered, it's always through this very long, elaborate process. All right. Where the energy source, it could be hydroelectric. In other words, you're relying on the gravitational potential energy of water as it falls to use that to spin a fancy fan called a turbine. And as you know, anytime that you spin a turbine, you cause an armature to spin, generating electricity. Okay. So most electricity is made this way. All right, it's by spinning an armature. So it doesn't matter if it's just water that's trickling down and spinning a paddle wheel, or if you're dealing with wind energy, where the wind's blowing against a fan, where it causes it to convert to electricity, or even as coal or nuclear. Because with coal and nuclear, you're generating a lot of heat. The heat is used to heat up water. The water turns into steam, and the pressure of the steam is used to, guess what? Spin an armature, all right? So that's the process that unfortunately we have to take in converting mechanical work into electricity. We currently don't have any more efficient method that we know of as of yet. Who knows? Maybe one of you guys will find a more efficient method. But this is our current technology that we have right now, right? Of converting heat or even gravitational potential energy into electrical currents. Electricity has one benefit compared to the rest of the forms of energy, and it's that you can transmit it through pieces of wire. So you're not physically transmitting any physical object, but the energy is still being able to be delivered from point A to point B. All right. But in order to deliver the energy from point A to point B, we need to do it very efficiently. I'm not sure if you guys have ever used an extension cord before, but with extension cords, you'll notice that your equipment struggles with it. All right. So for example, if you're operating like a table saw in your backyard and you connect it to an extension cord before turning it on, you'll notice the engine is struggling so hard as it spins up. It'll be growling as it accelerates, as opposed to if you connect it directly into the wall and then you turn it on, where it spins up almost instantaneously. All right. And that's the problem about wires. Wires have a resistance or an internal resistance, meaning you're going to lose a lot of it in the form of heat. So in today's episode, we're going to talk about ways to reduce all that energy wasted. And that's why we have to do this weird hack of stepping up the voltage up to 500,000 volts. Okay. Just a bit of background. You guys have probably seen these transformer stations before, or substations like that. Okay. Now, this is the one that's near my school, where if you want me to draw a map here, if you're familiar with the area, this is along Highway 7. And you know what? There's a lot of substations along Highway 7, right? For example, those that live towards the more central area, just between Yonge and what's beside Yonge? Dufferin? No, Bayview. Dufferin and Bayview on Highway 7, you'll see something like that. Now, that picture over there is all the way on the other side of Highway 7 and Markham Road, all right? Where if you go south of the ETR, you'll see that substation right there. So that's just a picture of the substation here. And you can see something very similar somewhere right over here as well. Okay. Yes, they're unsightly, but they serve a purpose of bringing down approximately 500,000 volts down to around 40,000 volts. Again, 40,000 volts is still too lethal for human beings. So they're going to drop it down even further. In fact, the network is in such a way that it looks like this picture here, right? So you have this generating station, whatever it may be, whether if it's hydroelectric, nuclear, fossil fuels, whatever it may be, it generates the electricity. But if you leave it at 120 volts, it's not going to make it to the destination after, a couple of kilometers. All right, the voltage drop will be too great because of the resistance of the wires. So what they do is they step it up to ridiculously high voltages. Remember, that's 500,000 volts. Okay, and at the end of the 500,000 volts, so that's what we have over here. Okay. 500,000 volts floating in the sky right there. Okay, we wanted to bring it down to the residential neighborhood, which means we need to bring it down to a safer voltage, such as around 40,000 volts. Again, 40,000 volts is still too dangerous for us. So they drop it down to around 4,000. Where is it? Oh yeah, there, 4,000 volts. Okay, and then that's where your green box is. Your green box will convert the 4,000 volts down to 120 volts. So the transmission towers, you've seen them before. The transformer substations, if you drive along Highway 7, you're bound to have seen quite a few of them already. Okay. And lastly, those green boxes or the gray boxes hanging up in the poles. You've seen those as well. So the question is, where is this mystery substation? And that's the thing. Substations, they're hidden in your neighborhood, sometimes right in your plain sight. This awesome YouTuber will show you where you can find one near the Finch train station. So the last thing that any neighborhood would want is for 500,000 volts to be running through their neighborhood. It's rather dangerous, arcing may occur, so they have to actually bring the voltage down to something safe, like around 40,000 volts. And the way how they do this is through a station called a substation. And the substation obviously will have equipment, and it's rather unsightly, and no neighborhood would ever want to have it. So they'll actually hide the substations in the form of a house, like this guy back here. You can see it's boarded up. There's actually a do not cross sign in there as well, but the equipment is actually visible from the backyard. So let's check it out. Again, it looks like an ordinary house in a rather ordinary neighborhood. Nothing special about it. And there's a fence there. I'm not going to try jumping over it, but we'll take a quick peek-sees. And if you look at the back of the house, it's actually exposed. And there's all the equipment. Pretty neat, isn't it? Okay, so why are we doing this crazy network? Why are we bringing up the voltages up to, 500,000 volts and then slowly bringing it down? Why not just give what the customer needs? Like, for example, with USB uses 5 volts. Why not just transmit 5 volts from the hydro line right to your house so you can just charge your cell phone because you're not using 120 volts for anything else, let's say. Okay, so why this crazy science? Let's go and explain this. For one thing, most technology relies upon current flow. So current is the reason why it works. For example, stove elements, they only get hot because of current. It's not because of voltage. All right. The same thing is also true with regards to motors. Anything that relies upon a motor, such as the motor that's used to compress the gas to make your air conditioner work, or to even make your refrigerator work, that coolant gas, the refrigerant, it needs current as well. If you recall, F is equal to current times the B field intensity. So you need to have a strong magnetic field, and you need to have current in order for it to generate a force, okay? So that it can convert electricity into work, all right? So we need current at home. That's what we need high of. We don't really care much about the voltage. But here's the thing. Loss of power in hydro lines are because of the lines heating up because of high current flow. Remember, current is what results in heat dissipation. So to minimize power loss, what will they do? They're going to try to minimize current as much as possible in the transmission line. So I'll give you guys a moment to jot this diagram down, and some people will be wondering what this little scribble is over here. It's just a fancy way of saying it's a very long line. That's all. So if you choose not to draw that, that's fine, all right? It just tells you that's a very long line. And because wires have a resistance, often it's modeled with a resistor. Okay, so that resistor there is placed in there to tell the reader that, yeah, these lines are not superconductors. You lose a little bit there. Another thing is that most loads, they just characteristically behave as a resistor, regardless if they're efficient or not. In fact, in their most inefficiencies, I suppose, or efficiencies, however you want to take of it, if you ever had a baseboard heater in your house, the weird piece of metal that, if you fall into it, you'll get a scar in your head, like how I did as a kid. All right. Those rely just upon short-circuiting your electricity in your house. All that's in there is just a huge resistor. So the resistor is converting all that voltage or all that current into heat and heating up your room. All right, it's an expensive way of heating up your house, but it's one of the old school ways of doing it. So the houses that are, 40 years plus, maybe even 50 years old, they may still use baseboard heaters. All right, I hope that's enough time for you to jot it down. The slide will remain up for a while as well. All right, just wanted to give enough time for most people to jot down what is needed to be jotted down. So this is an example where, let's say the power station tries to deliver 1,000 watts as is. All right, so I'm going to transmit it at, I'm just keeping the numbers nice and clean, 100 volts. Okay, and you're hoping that on the far end, the device is hoping to accept 100 volts. Now, the reality is it's not. All right, you're going to lose some of it here, and you're going to end up with whatever that remains here, whatever that amount that may be. Okay, so you're going to lose a little bit in your transmission line because your transmission line has a measurable resistance. And that's all that's given to us so far. It's transmission characteristics and the resistivity of the line itself, which we'll just say that it's roughly at 1 ohm of the line. Okay, so that's the transmit and return path. We're just summing it all up together. All right, so let's figure out what the power loss is here. First off, if you look at the problem here, we're not given enough information in general, right? There's no way to solve any individual thing immediately. What we can solve at first, at least, is the current that's being delivered in the setup. So since we have power and we have voltage, we can divide power by voltage to determine current. So the current is equal to 1,000 watts divided by 100 volts. What that tells us is that in this setup over here, 10 amps is being delivered throughout the entire circuit. So 10 amps at the beginning, 10 amps through the line itself, 10 amps successfully through the load, and 10 amps will return back to the source again. All right, so we're not violating any form of conservation right here. And now we have enough information to describe the transmission line. Remember, as long as you have two givens, you can solve for the rest of it. I know that right now, with the two formulas we know so far, which is P equals IV and V equals IR, neither of these two formulas individually can help us solve for power, but we can use them together in unison to solve for it. All right. For example, here, all that's given to us is current and resistance. We're not given a voltage, but we know that we can multiply current by resistance to give us voltage and sub the voltage into here to give us the power. So you could go through this two-step process. You could first figure out the voltage drop across the transmission line and then use that to find out the power. Or you can just simply sub in equation 2 into equation 1. And when you sub it in, initially you get P is equal to I times R. But out of simplicity, why not just simply call it P equals I squared R? Okay. Knowing that your power loss, which is the power that's going to be dissipated by the line itself, is going to be equal to I squared R, and you already have I, and you already have R, you could just simply sub it in and crunch it through. And in our calculations here, you'll notice that the power loss is 100 watts. That was lost. We start off with 1,000 watts. Remember, this thing gave away 1,000 watts to the world. This guy used up 100 watts in heating up the line, meaning that at your destination, you only received 900 watts. All right, so this system over here is only 90% efficient. Ideally, you want it to be close to 100% efficient. In other words, you don't want to lose that much here. And 100 watts is quite a bit. If you guys ever had an easy bake oven, if you ever looked in the inside, you'll notice that what's in there is a 100-watt light bulb. So you're using a light bulb to cook your food, literally. All right. Why do they choose that? Because it's just so easy to build, right? You just take a little plastic box, make sure it can thermally handle the heat, screw a light bulb in there, sell it to a bunch of kids for an inflated price, and both parties win. All right. And a 100-watt light bulb, if you ever touched it with your hands before, yeah, it hurts, but it's not going to give you any serious burns. Maybe 3rd degree if you hold it for long enough, but otherwise you'll probably react quickly enough to realize that, hey, this is hot, I don't want to touch it, and you'll move your hand away. The reason why I'm sharing you that story is that a 100-watt light bulb is only 5% efficient. In other words, with a 100-watt light bulb, 95 watts of it is given away as heat. I just wanted you to appreciate how hot 100 watts is. Okay, take an easy bake oven, stick your hand in there. That's 100 watts being wasted by turning it on, the circuit on at all times. All right, so even though this is 90% efficient, we're wasting a lot of heat away. That is being dumped away. So watch out for that. Okay, so how can we reduce that wastage? As it described up here, energy is being wasted by heating up the lines, and the heat comes from the current flowing through the line itself. In fact, if you take a look at the formula over here, let's take a look at correlations. What is the main contributing factor in power loss? Current or resistance? And after you've explained that, why? And you can see it all from the equation. Squared, that's it, okay? This is the reason why. Okay, so your power loss is mainly contributed towards this evil squared thing. Power loss is correlated to current squared. Meanwhile, power loss is only directly or linearly correlated to resistance. Okay, so if your resistance doubles, yeah, your power loss is double. That's just a fact of life. But if your current doubles over here, your power increases by 4 times. So this is the big elephant in the room. So even though resistance, we can't really do much about it because we have yet to build a superconductor that can operate at proper room temperature. I know there's quote unquote room temperature right now if you've read those scientific journals, but those are under room temperature, as in it's in the middle of winter room temperature, and you need to have two big pieces of diamond squishing against it to make it a superconductor. Okay, it's not practical over 100 kilometers or so. All right, so that's the reality. We always have resistance in the line, so we can't do much about that. But this, maybe we can do something about that to make the wastage less of a big deal. So this is a very similar story as before. Okay, we have a transmission line or a transmission power source where they're still trying to deliver 1,000 watts. But this time around, let's see how much of it makes it to the end. Okay, how many are lucky enough to get to the far side? So in this setup over here, it's slightly different than before because now we have two transformers. We have the first transformer on the left, which steps up the voltage but causes the current to drop. And then on the far side, probably 100 kilometers away or so, we drop down the voltage and then bring back up the current because, as I said, most devices need current to operate, not really voltage. Once again, as a reminder, anytime the voltage goes up, it's classified as a step-up transformer. And that's what they have in most transmission lines or power transmission stations. Okay, they bring up the voltage up to very high voltages, as high as 500,000 volts. Then they transmit it over up to 100 kilometers or so. And then they drop the voltage down to something that's a lot safer so that in case if you touch it, you'll still survive. I mean, I could probably ask you guys to raise your hands. How many of you guys have been electrocuted by 120 volts before? Just the two of us? I'm sure there's more of us that have felt the shock before. All right. And hey, look at that. We're able to raise our hand up. And that's the thing about 120 volts. You can survive under it. All right. Unless if you have a very weak heart or you have other physical issues, you'll survive with 100 volts. You might curse and swear afterwards and have a sore arm, but that's about it. Okay. So 100 volts is relatively safe. 500,000 volts, you're not coming out of that one, unfortunately. All right. So that's why we don't deliver 500,000 volts into the house. We have to gradually bring it back down. Okay, so let's just use this super simplified example just to show you how much more efficient this little setup is. All right, so this is a setup where I didn't give you too much information. I just simply said that we started off with 1,000 watts, and then we're going to bring up the voltages up to something that's incredibly high. Let's say we're going to bring it up to 100,000 volts now. So in the past, we only had it at 100 volts. Now we increase the voltage by 1,000 times. And as a consequence, when the voltage goes up by 1,000 times, the current has to drop by 1,000 times as well. So if you recall in the previous example, we had 10 amperes of current. Let's go and do the math right now, and you can see that the math still correlates. Once again, power is equal to current times voltage. So when you isolate for current, you divide your 1,000 watts by 100,000 volts. In the previous example, we had 10 amperes. This time round, you'll notice it drops down to 10 milliamperes. Again, to find out the power that's being dissipated by the line itself, because we know the current and we know the resistance, yes, we could use V equals I times R. All right. And with that V, we know that P is equal to I times V. So we can sub that into here and get a bigger formula, which looks like this. Power loss is equal to I squared R. We then substitute in the 0.1 amperes into the I and the resistance of 1 ohm, just as our reference value. And look at that now. In the previous example, we had an easy bake oven of heat being released. Now we have something that is almost negligible. Okay. In fact, if you want to look at your percentage power loss, is that even typed out here? No, it's not. So I'll just go through this. Okay. What is your percentage power loss? Well, that's just equal to your power loss divided by your power that's been delivered, your power input. Okay, you're going to multiply it by 100%. So in the original one, if you recall, we lost 100 watts out of 1,000. Okay, and that's why our percentage power loss was 10%. So it was 90% efficient, but we lost 10% of it. In this case over here, we're using a very small number now, 0.001 watt versus still the same 1,000 watt condition. So you take out your fancy calculator, 0.0001 divided by 1,000, multiplied by 100 to convert into a percentage, And look at that percentage there. It's a crazy small percentage. 0. How many zeros? That's 4 zeros. So your percentage power loss is 0.12341%. Look at that. Before we had a 10% loss, and now it's almost negligible. And that is the science of the reason of why we go off and do this crazy thing over here. That's why we bring up the voltages out to some high astounding value. Because at high voltages, your current is very low. If you know that current is the reason for power loss, then that's why you want to minimize current. Lastly, the only way to bring up the voltages efficiently with something that you can make in your own basement, you want a contraption that all you need is wires and metal. And that, my friends, is called a transformer. All right. So a transformer allows you to bring up the voltages up to a crazy high voltage, and it allows you to bring the voltages down to something that's a lot safer. And the last piece of the puzzle, why in the world are we using AC current in the house? AC current is the only reason why transformers to work. Because if we want the system to be efficient, first off, we need to convert it to AC current so that this guy here works to bring it up to high voltage. We bring the high voltage across to minimize current loss. And on the far side, so that it's safe to use, we have to bring down the voltage by using another transformer to bring it down to something safe, like 120 volts, to go into your house. And eventually, you'll have those little wall things, like this guy here, since I'm not using it, to finally bring down it from 120 volts down to a safe 5 volts so you could charge your cell phone or power up your camera like how I am right here. As I said, it will take the entire unit to explain why you need AC in your house, and that's the reason why. AC current is required for this gizmo here to work so that we can have efficiencies in delivering electricity. There's your story. I don't think anyone else needs this, and now you have a better appreciation of why our infrastructure is set up the way it is. In fact, if you go back into a bit of history, there was this whole big fight between Thomas Edison and Nikola Tesla, right? Both of these guys, not only were they super geeks, they were also super savvy businessmen. They wanted their names to be in the history records, and they wanted to become, forever famous that way, right? So, the biggest market at that point when they were around was, how do you deliver energy to a house? Because a lot of people, they just slept at night with just candlelight and that's it. And now look at this. I'm living in a basement and I'm having all this almost unlimited power supply in here. All right, where I have the equivalent of 80 servants serving me each and every day. If you do the math for it, an average person uses about that much power. The equivalent power of 80 people doing work for you. Okay, so they were both fighting about, how do you get the energy from point A to point B? Thomas Edison said DC is the way to go, but however, DC won't allow this to work. Nikola Tesla says, no, there's better efficient ways. So he says, hey, let's use this infrastructure. And for the next 100 plus years ever since, we've been following that infrastructure. And in the States, because they made 120 volts the standard a long time ago, it just became the norm. In fact, the norm initially, I think, was at 100 volts, and they gradually brought up to 120, which is what we have nominally today, right? And yes, out there in Europe and in Asia, they created their standard at 240 volts, but that's because they stabilized that infrastructure at that point there, and that's why they stick with it. Okay, on to the next few slides. Oh, one more cool thing just to explain to you guys. Many of you guys might think that you only get 120 volts in the house and that's it. And that's not really true. In fact, every house has 240 volts. If you ever seen the plug of, for example, your clothes dryer, hey, you know what? We're here right now. Why won't I just show you that right here? Here you go. That thing. All right. That is the plug for my clothes dryer. All right. And if you measure the voltage there, that is at 240 volts. So we do get 240 volts in the house. All right. Because again, with a higher voltage, we can compromise and allow more current to flow through as well. All right. So anything that requires a high amount of power, in order to accommodate that without too much current going to your house, you have to increase the voltage. So there are, as far as I know, 3 devices that rely upon that right now. Okay. Your clothes dryer needs it. Your stove, if you have an electric stove, it needs 240 volts. And many times these days, we have electric cars in the garage. So they'll retransfer that 240 volts and carry it right into their garage as well. So we naturally do have 240 volts, but they're connected in series, as you can see over here. Okay, so we have 2 separate phases. All right, we have a phase on top for 120 volts, and we have another phase down below for another 120 volts. And if we connect them together from end to end, that's how we get 240 volts. Okay, so we do get 240 in the house. It's just that not too many appliances need that right now. Okay, so the last bit of story, all right, the finishing story, which is on the world of hydro bills, all right, and let's do all the calculations for it. First off, hydro bills, they're measured as a cost rating in kilowatt hours. And as I mentioned, energy can be measured using pretty much 3 or 4 units in total, all right. If you're dealing with very small, minuscule values, you'll be counting them in electron volts, something we learned in the previous unit. And yeah, if you needed 1,000,000 electron volts, so let it be. It's still a minute small quantity of energy. If you need to boost it up a bit more, because you're measuring it in an order of magnitude of, I think, 1 to the 13 or so, then yeah, you'll measure it in joules. So you need 10 million times more in quantity, you'll measure it in joules. You could also measure it in calories, because a calorie is equal to 4,000 joules, so you can scale up with that. However, with regards to household electricity, as I mentioned, you have about anywhere from 40 to 80 servants working for you in your house all at once right now. So in other words, if you hired 40 to 80 people to sit on those bicycles to pump electricity, that's what you're getting in your house, as well as for the heat in your house. Okay, we're using a lot of energy here in North America. All right, and in those large quantities, these things are just way too small to count them. So we count them in kilowatt hours. So a kilowatt hour is a measurement of energy. I know the name has the word watt in it, and people get confused and think that's a measurement of power, but no, it's an energy usage rating. And to prove it to you, let's derive it out. Okay, what exactly is 1 kilowatt hour equal to? We'll place it as 1 kilowatt hour over 1, because we're going to multiply it by all these ratios. We know that in 1 hour, there are 3,600 seconds, just to get hours out of the way. Another thing just for me to change right now is that a watt is equal to a joule per second. So that way you can see how the seconds cancel out. The other unit that we need to get rid of is K. And we know that K means 1,000. So really we're doing 1 times 3,600 times 1,000, and we get 3,600,000. And if you look at the units, hours cancels out, seconds cancels out, K cancels out, and we're left with just J on top. And that's the answer to one of your review questions from the previous unit. Okay, so a kilowatt hour is a measurement of energy, an insanely high amount of energy. 3.6 megajoules is equal to 1 kilowatt hour. Okay, and as you may know, your hydro bills, it's relatively cheap for this amount of energy. Right, this energy over here, again, they're charging somewhere in the realms of less than a quarter for it. Okay, so it's less than 25 cents for that many kilowatt hours. As I mentioned right from the beginning of this course, right, if you take a water bottle and you lift it up by 20 centimeters, that's 1 joule. That's 1 joule. Do this 3.6 million times. That's 1 kilowatt hour of effort. Okay, and that only costs you 25 cents in electricity. So in general, electricity is cheap, but it does add up sure quickly. And that's what we're going to do right now. We're going to go through those calculations. Okay, to simplify our time, drop anything that's written in blue, because you don't need to write that down to get to your end statement. All right, but let's just go back to this. Let's say that we haven't upgraded to LED lighting yet. All right, so we're still using these high current draining or high power draining light bulbs. And again, you're not using just one of them in your basement. If you go to Home Depot or whatnot, you end up buying them as a 6-pack. All right, so that's why you always end up having them in 6 sets at a time. So if you're turning on all 6 at once, you're really draining 300 watts. Okay, and let's say that you're spending your life right now just living in the basement because of the current conditions. So the question is, how much is electricity costing you living in a basement using this premium lighting? So let's go do the math. Okay, so 8 hours a day times every single day in the year is about 3,000 hours where it's turned on. And you know that electricity is always charged per kilowatt hour. Let's say that it's right now at 16.1 cents per kilowatt hour. Okay, so the first thing we got to figure out is, how many kilowatt hours have we consumed so far? And it may seem like it's a rather complicated formula, but it's actually pretty straightforward. All right, we know that energy used is equal to power times time. So in this case over here, our power is 300 watts and our time is 2920 hours. If you multiply these two together right now, you end up getting a number of, what is it? 876,000, and look at the units, watt hours. And to simply convert it into kilowatt hours, in your head, just erase 3 of the zeros, and booyah, There you have it, 876 kilowatt hours. It's not a very challenging calculation there. Even the next part, I know it's not an official formula to write down, but you already know that if you consume something, it's always the cost per unit times how many units you use, right? And you can treat it the same with regards to electricity. How much have you used and what's the rate for that usage? So you used up 876 kilowatt hours and the rate is at 16.1 cents per kilowatt hour. So you calculate that away and you get an awesome $141. And yeah, that's quite the pretty penny just to heat up that, or just to turn on lights for that one room in your house. Never mind all the rest of your rooms in your house and the washroom and turning on a TV and any other devices you have. Okay, so whenever your parents are screaming at you to turn off your lights when you're not in the room, that's the reason why. In fact, that's only half the reason why. Okay, so here's the reason why your parents are going nuts over you using too much electricity. It's because that number over here, it may seem, rather innocent, like, oh, that's not the end of the world. That's only probably 2 video games. Well, in truth, it ends up costing a lot more than that. If you take a look at your hydroelectrical bill, there are all these extra surcharges. Now, I know this picture is not the best picture of them all, but if you look back into your old grade 9 textbook, I copied and pasted this from there, all right? Where in that textbook, the initial charge for that month was $154. Of course, when you look at the real tally at the bottom, and Mr. Maciel can also contest to this, it pretty much inflates to double the amount. And that's the end reality. So why does this happen? And there are a lot of reasons for it. Many of you guys might think, oh, it's because of GST and PST, but there are other reasons. We already described the fact that there's no super efficient system out there. Even transformers lose a bit of energy in the form of heat. All right. So as the energy is being delivered, somebody has to pay for all those losses in heat. And guess who gets to pay for it? Whoever that lives in that house. In fact, someone else I talked to that owned a cottage, they noticed that the difference between this value here and the value down here inflated by as much as 4 times, and it's because of the delivery charges. All right, so somebody has to pay for that loss in energy. There is unfortunately no free lunch. Okay, and also the fact that if you ever seen those transformers explode, somebody eventually has to pay for it. Remember that cost of 16 cents per kilowatt hour is just the cost of electricity, and that's it. It does not factor in anything else. Okay, so they have to have this reserve money so that they can do the repairs that needs to be done. Whether if the lines need to be upgraded, buried underground, transformers replaced, they need that. So it has to be factored in there in the calculation somehow. There's also our previous hydro system which has become defunct, and we had to slowly pay back into it. I know that we're almost fully paid back by now. In fact, it could be completely cleared, but at some point that was a big factor, all right? And that's why our costs did elevate. And lastly, GST and PST. All right, so there are many reasons why the values increase, and that's why your parents are very frustrated when you leave the lights on. So I hope that that's the last PSA message for you guys, and you'll appreciate that. When you're not in a room, turn it off, because the couple of cents you save at the beginning will become lots of money at the end. Make sure you do your homework in your course pack, page 61 through 8.